Okay, so thank you and welcome to everyone. And I would like firstly to thank the organizer of this nice series of seminar for inviting me today. And today I will talk about mainly the results that I had and I published during my PhD thesis. And I entitled this topic, this small seminar, a density-corrected DFT scheme applied to the calculation of spin state energetics. So in the following, I will focus mainly on octahedrali coordinated iron 2 complexes. These compounds, in fact, the electronic structure of the D block consists of two degenerate electronic states, a threefold degenerate T2G non-bonding state, and a twofold degenerate EG state. So the magnetic ground state in these compounds is the result of the competition between the ligand field splitting delta between the EG and T2G states and the electronic repulsion pi between two electrons sitting on the same electronic level. So because our aim is to study spin crossover phenomena, that are phenomena in which the magnetic ground state, the magnetic state of a certain compound can be changed by means of external stimuli such as temperature, pressure, light, and magnetic field. It is crucial for us to compute the adiabatic energy difference for this between these two spin states. And it is a well-known fact that the evaluation of this quantity by means of electronic structure methods it represents a great challenge. In fact, this difficulty stems from the lack of error cancellation when we compute the total energy of spin configuration that exhibit different amount and type of electronic correlation. More specifically, in the low spin state, we expect higher, more intense effect of dynamical correlation. This is because the higher number of W-occupied electronic states, and as well as for what concern non-dynamical or statical correlation, the low spin state, because of the higher number of bonding states, exhibit a more multi-configurational character of the electronic wave function. And moreover, this multi-configurational character depends on the ligand field strength of the compound. Here, I plot the principal weight of the expansion of the KCF wave function for a set of 4 iron 2 complexes for increasing ligand field strength. And as we can see here, the multi-configurational character of the wave function increases for stronger ligand field strength compounds. So because our aim is that of studying spin crossover phenomena in spin crossover meta-organic frameworks, we need a reliable DFT approach to study this system that cannot otherwise studied by means of high quantum chemistry method. So the problem in DFT is that different exchange and correlation functional would lead to significant different values of the computed delta E. For example, it is a well-known fact that local and semilocal functionals would tend to overstabilize low spin over high spin. On the correct description of spin energetic by means of hybrid functionals, introducing a certain amount of exact exchange accordingly to the system under investigation. In fact, the amount of exact exchange needed to achieve a good description of the energetics depends on the ligand field of the complex under investigation. A similar effect on the energetics is observed when an Hubbard correction is used on the top of local or semilocal functional. In fact, the effect of U is, as in the case of hybrid functional, that of stabilizing high spin over low spin state, with in principle the advantage represented by the fact that the Hubbard parameters that has to be introduced in the calculation can be computed in an ab initio fashion. So like a small introduction to DFT plus U. So the idea is that we want to model the DFT functional on the Hubbard model. So in fact, this model has been introduced to treat system characterized by strongly correlated electrons, and in particular to describe multi-insulators. In this system, in fact, the insulator ground state is because a gap between bands of like character opens due to the strong electron-electron interaction. So the idea in DFT plus U is that of starting from defining the occupation of the selected subshell, so the strongly correlated subshell that we are considered, in our case, is the 3D levels of the iron, through a projection operation of the Consham state, occupied Consham state, into a suitable choice of a localized base. So in DFT, standard local and semilocal functional, that wrongly predict multi-insulators to be metallic, the computed values of the occupation matrix elements result to be fractional. This, in fact, represent and are due to the wrongly described metallic phase in these systems. In DFT plus U, the idea is that we can introduce an Hubbard potential that force the occupation to be either 0 or 1, so opens the gap, and in the expression of the total energy, an Hubbard energy term that penalizes fractional occupancies is added. And as I anticipated before, in this formalism, the Hubbard U parameter potential can be computed ab initio as the global curvature of the total energy with respect to the occupation of the selected subshell. So moreover, in general, the DFT plus U method improved the description of localized 3D electrons by recovering the exchange and correlation potential and alleviating the self-interaction error. So it's for this reason that we want to try and to test the performances of LDA plus U and PB plus U, where the Hubbard U parameter is computed in a self-consistent scheme, and their performances in evaluating the delta E for a set of 6 iron-2 complexes ranging from weak ligand to strong ligand. So in the following, I will refer to these 6 compounds just with the name of the relative ligand. And we use as a reference value the delta E computed with CASPT2 corrected couple cluster method. This method, in fact, has been introduced in 2018 by Pierre, and the idea is that of merging the CASPT2 method with the couple cluster. So the total adiabatic energy difference is the sum of the CASPT2 delta E plus the effect of the electronic correlation from the 3s-3p levels computed with couple cluster. So as expected, the PB functional overestimates delta E for all the molecules. But despite of this, we can see that at least this functional is able to reproduce the trend of the values across the series. So for increasing ligand field strength, the gap between the two spin states is expected to increase with along the series. On the contrary, when we analyze the values obtained with PB plus U, we see that not only the overall error is larger compared to PB, but PB plus U actually is not able neither to describe the evolution of delta E across the series. And when we test, similar results actually are obtained when we use LDA and LDA plus U with the difference of a rigid shift to higher energy. So we ask why PB plus U fails in computing delta E, while it's a method that is in principle supposed to improve over the standard PB functional. So here, if we write down the expression of the DFT plus U energy, then and the relative delta E computed with DFT plus U, we can see that the difference between the Hubbard energies in high spin and low spin strongly contributes in the evaluation of the final value of delta E. And this term always penalizes low spin state. This penalization increases along the series, giving rise to this almost flat series of values. And its contribution to the total delta E can reach up to 6 EV in the case of the stronger ligand field complex. So why EDU is always larger in low spin? Well, by analyzing the expression of the EDU energy, we can see that this unbalanced description of the two spin states arise from the summation term being systematically larger in low spin compared to high spin, and the difference between these two contribution in the two spin state increases with the ligand field strength. So at this point, so like the summation term, of course, is proportional to the fractionality, so the fractional values of the occupation matrix element. And as to be noticed at this point that even though in the case of Mott insulators, fractional occupancies were associated with a metallic behavior, here fractional occupancies are because of the strong hybridization between the iron and the ligand states. And more specifically, if we divide and decompose the summation term contribution into the T2G and the EG-like Consham electronic states, we can see that the most intense, the major contribution arises from the EG state. So for this reason, I will take as an example and analyze how the occupation matrix elements are computed in the case of the DZ square EG state. That, of course, in an atomic-like picture would lead to an occupation matrix element equal to 0. Well, when we pass to a molecular orbital picture, we can see that, like as expected from the theory, the 3D electrons and the ligand electrons mixed together give rise to an antibonding unoccupied EG star state and a bonding EG occupied state. And at this point, if we compute the occupation element, the occupation of this state, then we obtain a deviation from 0 that is proportional to the D-like character of the occupied EG state. So when we pass to stronger ligand field complexes, for example, CO, of course, the D-like character of the occupied EG state increases as well, giving rise to occupation matrix element larger compared to the case of the weak ligand cases, and a summation term that is larger as well. So here we can see why we see this trend across the series from weak ligand to strong ligand. Well, now if we analyze the situation in the high spin state, firstly, we can analyze firstly the spin down channel, then the spin up channel. So for the spin down channel, the DZ square orbital is unoccupied, and the situation is similar to that just discussed for the case of low spin state. In the spin-up case, by the way, the situation is different because both the EG star and the EG orbitals are occupied. So the projection operation through which this element is computed give rise to a value that is always almost equal to 1, because the D-like character of the two occupied states sum up together. And the summation term, the resulting summation term, is close to 0. So we can see at this point why there is this unbalanced description and this bias toward the spin, because in high spin only one spin channel is contributing to the Hubbard energy. So we are introducing a bias in all the computed delta E. So, but what about the density in the DFT plus U theory? Well, it's a well-known fact that in exact DFT, the profile of the total energy with respect to a fractional number of electrons is represented with a spurious curvature of the energy. So we can measure the quality of the density or the amount of set interaction error by computing the deviation from linearity of the functional under investigation. So we did so for PB, here represented as thick lines, and PB plus U, the thin lines. And as we can see, the introduction of the Hubbard term systematically improve the quality of the electronic density. So to summarize what we said up to now so far, so the Hubbard energy term in DFT plus U is the responsible for the observed bias toward the spin. This bias increasing with the ligand field strength completely hides the evolution of the adiabatic energy difference across the series. But despite these drawbacks, the electronic density is systematically improved. So the idea is that to merge these ideas and try to develop an approach that can help us to keep the improved electronic description, the improved electronic density obtained with the DFT plus U method, while at the same time removing the bias toward the spin. This in a density-corrected DFT scheme. So more precisely, what we want to tackle this problem by means of non-self-consistent DFT, where the total DFT energy is computed on top of electronic density that does not represent the self-consistent one, and that it is possibly better. So our working hypothesis is that of using a PB functional and feed it with a PB plus U electronic density. So practically, this is quite easy to implement. In fact, if we have a look at the expression of the DFT plus U energy, we can expect to recover this quantity only not considering actually the Hubbard energy term. In fact, the remaining term represent with good approximation the DFT plus DFT energy computed on the top of the DFT plus U density. So this approach actually has been also motivated by a recent work of Burke et al. From 2018, in which by analyzing the performances of DFT in evaluation the delta E for iron 2 complexes, they conclude that this kind of calculation are affected by density-driven error. So what does it mean? It's quite simple. So if we can divide the total DFT error, of course, in the situation in which we knew the exact DFT functional and the exact, the relative exact electronic density, then we can divide this error in a functional contribution and a density contribution. So in most of the DFT calculation, the error introduced by the use, by the approximation on the energy functional is larger compared to that of the inaccuracy of the electronic density. While there is a subset of calculation that are defined as abnormal calculation, in which these two errors are comparable. And this is indeed the case for the evaluation of delta E. So here the result for our proposed Hubbard-corrected density approach. As we can see, the results actually show that the bias toward the spin is removed for all the complexes, and the computed delta E are in good agreement with our CASPT2 couple cluster reference. So an alternative way to remain in the framework of DFT plus U while treating system characterized by strong covalency is that of introducing an intersect potential V. This potential, in fact, results in a contribution in the total DFT plus U plus V energy that counterbalance the penalization for fractional occupancies due to the on-site U potential. So as expected, actually, this approach, so the introduction of the intersect V potential, reduced the bias toward the spin, but at the same time, the computed self-consistent values for the intersect potential V are too small compared to the on-site potential U, and so this bias is only partially removed. So to further validate our approach, then we compare the results obtained with different DFT functionals, so GGA, meta-GGA, hybrid, and meta-hybrid functionals. So among all the DFT functional tested here, the Hubbard-corrected approach is the best performer, followed by the meta-hybrid TPSSH with important that these conclusions strongly depends on the chosen reference method, so CASP-2 couple cluster. In fact, in literature, different authors have used different methods to compare the computed adiabatic energy differences. And so, for example, diffusion Monte Carlo or couple cluster. So just to like discuss a little bit this point, because golden standard for this kind of calculation. So what we can do now is like to consider the set of our complexes, dividing them between weak ligand and strong ligand complexes. Within the set of the weak ligand complexes, we can expect that the multi-configurational character of the wave function is small. And so couple cluster does represent a good standard reference method. And for these three compounds, CASP-2 and CASP-2 couple cluster match well with couple cluster, while diffusion Monte Carlo does not. So when we pass to strong ligand complexes, the situation is different because couple cluster no longer represent a good reference because of the strong multi-configurational character of the wave function. And in principle, both diffusion Monte Carlo and CASP-2 are able to capture these static correlations, but still the two methods result in a significant different result for delta E, almost 1 eV. And so in general, like we cannot conclude that which is the best reference method. So for our part, we just use the CASP-2 couple cluster for this kind of calculation. But in order to overcome the problem of produce an internal reference value, we studied also a set of 7 iron 2 complexes for which experimentally extracted data are available. So we test the performances of TPSSH, MO6L, and of course the Abadie-corrected density approach, that in this case, for the first 5 molecular crystal complexes, has been performed in periodic boundary conditions. So as we can see here, TPSSH systematically overestimate delta E, while both Abadie-corrected density approach and MO6L result in a main unsigned error smaller than 0.1 eV. Despite of this, both the methods are not able to capture the correct ground state for the first compound. So now let's pass analyzing the electronic density and the spatial distribution of the electronic density. For doing so, we compute the delta rho between 3 different approaches, PB, PB plus U, and Hartree-Fock, comparing them against the relaxed density obtained with CASP-2. So in Hartree-Fock theory that only treat exchange correlations, we are not able to capture neither the double shell radial correlation effect, that in fact the result is a density, an electronic density too much localized in the region of the metal center, neither the left-right correlation, that in fact the result electronic density is too much concentrated on the ligand. When we analyze the same plot with PB, we can see that the pattern is completely reversed. So this can be explained because, as it's been observed in several works in the past, the self-interaction error in local and semi-local functional tend to mimic and exaggerate non-dynamical correlation effect. For this reason that here we can see the complete opposite behavior with respect to Hartree-Fock. So when we apply an Abadie correction, while reducing the self-interaction error, what we are doing is also to improve the description of the electronic density around the metal center. So to summarize here, we tested and introduced the Abadie density-corrected DFT scheme. We show that the results for delta E, so adiabatic energy differences, are in very good agreement with both internal caspity-2 coupled cluster reference values and experimentally extracted data. The can be in periodic boundary conditions. And it's for this reason that I want to conclude just showing a result that has not been yet published. So we can use this approach to study extended crystals, metal organic spin crossover complexes. So we can compute the transition temperature. So I don't want to go into details because it's not the topic of the talk, but actually once we can compute the elements that enter, the terms that enter the expression of the free energy, then we can obtain the temperature at which we can expect a transition between low spin and high spin. So we evaluate the vibrational contribution from using PV functional and the adiabatic energy difference with a value-corrected density approach. And as we can see, we are able to obtain a transition temperature very close to the experimental one. So I would like to conclude, and thanks like Roberta Poloni and Vesla Isavlevich. Roberta has been my supervisor during my PhD thesis, and Bess has participated in most of the work of my PhD. And thanks for all of you for your attention.
Thank you very much, Lorenzo. So now it's time for questions. So if you have a question, please in the reaction section, click on the raise hand. So there, yes. If you have a question. Mathieu, go ahead.
Hi, thanks a lot. Very promising. Stay within DFT. At some point, you mentioned diffusion Monte Carlo in passing, and you threw it away just like the other methods. Is there a reason why it's not the gold standards compared to it's supposed to be for just about anything else, right?
Like when we compare, yes. To the point, yeah, there are several works in which, in fact, they have used diffusion Monte Carlo for computing this quantity and to produce the reference values. So at this point, I would say that both is quite arbitrarily the choice between diffusion Monte Carlo and caspity-2, because both the methods require some approximations. In one case, the active space, for example, for KCF calculation, and for diffusion Monte Carlo, the trial wave function. So there are a series of very nice work by Droghetti about the diffusion Monte Carlo calculation of delta E. And in fact, we can see that there is a dependency on the trial wave function. Actually, this is, I think, is still an open debate in the scientific community, which method one should use. So our analysis is based on the fact that we can say that coupled cluster is okay in describing weak ligand field complexes. So for these complexes, the result match well or better with caspity-2 with respect to compare with diffusion Monte Carlo. But still, like both the methods are in principle able to capture dynamical and non-dynamical correlation.
Okay, thanks.
Sorry, I was muted, sorry. There was a question first by David, I think. Then Gabriele, Matteo, and then Rex. I think that was, the correct order. Go ahead, David.
Thank you. So thanks Lorenzo, for this very valuable contribution, and actually a beautifully presented presentation, very clear and well prepared. So actually, Matthew beat me to the question about diffusion Monte Carlo, but I was wondering actually maybe there's something there. Actually, maybe the fixed node from PB is not a great place, and I wondered if the PB plus U fixed node would be a better starting point for DMC. But my question is actually if you want a physicist question, I haven't so far been able to find a clear definition of the distinction in the chemistry literature between static and non-static or dynamical correlation. And you gave a very intriguing sort of explanation at the beginning. I wonder, can you just, for somebody who can't find this definition, can you give a definition of the difference, or point me to a reference perhaps?
Yeah, in fact, like, it's not like, there's not like rigorous definition that we can use to divide statical and non-dynamical correlation. In fact, also couple cluster theory in principle is able to also capture what we call statical correlation if we go to higher orders. So we can, so going back. Yeah, so this point. So we can say but dynamical correlation are linked with the instantaneous interaction of the motion of electrons in the space. So somehow, like in this case, what I was saying is that in low spin state, because electrons are sharing, are packed in a smaller portion of space, they feel much more each other's. So we can say that this electron-electron interaction, instantaneous electron-electron interaction, is somehow linked with what we call dynamical correlation. And on the other side, non-dynamical correlation are the kind of electronic correlation that we can recover by introducing more determinants in our expansion of the wave function. So in principle, here, for example, a way in which we can have an idea of the amount of non-dynamical correlation is that of taking the principal, the weight of the main configuration in a CF expansion. So this means that, of course, if the main configuration would be 100%, that in that case, we don't have a multi-configurational character of the wave function. While when we move and we have the weight of the main CI coefficient, that becomes
Okay, thank you.
And then there was a question by Gabriele.
Yeah, I think I can go on. Hi, Lorenzo. Thank you very much for your nice talk. So you've been showing that the plus U correction to DFT, don't help to get a better spin state energetics, but they improve the density and that you can use in other calculation. You then mentioned in passing DFT plus U plus V, so with non-local, let's say, off-site interactions, saying that they don't help with the energetics. I just curiosity about if they improve the density or not.
So that in fact, if I go back.
And if I can just add, if it is something, the V terms that you can also compute ab initio, the second.
The V term, the intersect.
Yeah, second question.
Yeah. So to answer the first question, actually the effect of the intersect potential V is that of stabilizing the constant state that are otherwise destabilized. So the Hubbard potential actually is repulsive for states that are characterized by strong with fractional occupancies. And so the effect of V is that of being attractive for constant state that are for which the fractional occupation is due to a specific hybridization. So when we introduce the V, of course, we have to tell so we have to specify both the metal state and the ligand state that we want to treat explicitly. So in terms of density, actually, what we saw is that the V potential go in the, so counteracting the U potential, actually, it worsening the density slightly. Because if you can see here, for example, like the U is correcting, but is not correcting enough. So somehow you can think that the V is somehow counterbalancing the effect of U, also on the density. So you would obtain a pattern that is slightly, very, like, is almost, you cannot see by eye, but we saw by plotting the result that is much more close to PB. So it goes in the direction of PB, the effect of V. And yes, it can be computed ab initio.
Thanks.
Yeah.
Okay, so then there was a question by Matteo, and then after that there's Rex. Matteo?
Yes, can you hear me?
Yeah.
Okay. Yeah, thank you, Lorenzo, for the nice talk. I just wanted to ask something that you mentioned by the end of your talk. You mentioned the application to some extended periodic systems. Do you already have results for this system? You said unpublished.
Yeah, this system actually we still like actually we are working on MOF and
my question is obviously you're still looking at the relative energetics of two different spin states, right? That's what you're interested in. Have you tried doing the same with comparing different states? I mean, I'm asking this because I tried using your same approach in comparing the energetics of two states that had different oxidation state rather than different spin states. And I got opposite answer to yours. So meaning that if I density corrected, I get worse result. I actually get as plain PB gives. Okay. So I get no correction with respect to PB, while the agreement with experiment from the self-consistent but correction seems better. So I was wondering if you've tried other things than spin crossovers.
Not yet, actually. We tried other spin states. So the comparison between different spin states, yes. Different oxidation states, not yet. So if you said that like you find some not like improvement using this approach, basically. Yeah, I should test. Yeah, which kind of system are you?
Well, I was doing a system totally different than yours. I mean, systems for lithium-ion cathodes, battery material. So where the transition metal changes its oxidation state, so depending on how much lithium you have in the structure, obviously.
But of course, there's also like as I mentioned before, and this is like a topic. Also, the last seminar here was somehow about like the idea of that there are some class of calculation that are affected by density driven. So I don't know if this is the case for you. So like in most of the system, the improving, let's say, the density, but keeping the same functional would not affect that much the result of the calculation. So in that series, actually, there are like a very nice series of work by Burke et al. So they propose like to use like, for example, Hartree-Fock density, etc. But of course, if the system and the problem is not affected by density-driven error, then the difference is very small. So I guess if probably like your case is not affected by density-driven error.
Yeah. But is there, as far as you know, is there only, let's say, a catalog to understand which system belongs to which category, or is there a rationale that helps us?
So actually, I would say like the best way would be like to test and to try. If you try to do like a non-self-consistent calculation, like replacing the input density, not like particularly with the PB plus U density, but for example, you can try to replace the Hartree-Fock density. So like feed a PB function with an Hartree-Fock density. And you can see like if this the result change a lot, so possibly you are dealing with a problem that is affected by density-driven error. Otherwise, probably like if you change the functional, you can improve much faster and like you can improve more the result of your calculations. This is what's suggested by working like I can give you the.
Yeah, no, I took note, so you don't need to go back.
A nice theory about it. And so like the idea is that like if you test with other densities and you see a significant difference, that probably is the case of a density-driven error problem, like affected by density-driven error.
Okay, thanks a lot.
Thank you.
There was a question by Rex.
Yes, thank you, Lorenzo. You mentioned this nice decomposition by Burke and Perdue and others into density-driven error in the energy and functional-driven error in the energy. Mm-hmm. Now, presumably, one might well want to perform a calculation for a system in which your transitional metal complexes are part of a larger system, and that other parts of the system might not be dominated by density-driven error, by functional-driven error. What would happen, do you think, if you applied your method of correction to a larger system?
Okay, so if I understood, like you're saying, if for example we would like to use the DFT plus U density by changing the functional, so which is the effect of changing the functional? This was is your question, probably.
Yeah, that would be a good start. Yeah.
yeah. So like if you are treating like a big system in which, for example, PB plus U or PB is not enough, if you can like use the PB plus U density along with another functional, well, in principle, yes, like you could try. Of course, like then the PB plus U density, of course, is like correcting the density around the metal center. So you cannot expect that the density is much more different with respect to the PB one far from the metal center. I think.
Okay, thanks very much.
Okay, just before we move on to the next question, I just want to point out that there's a comment in the chat by Marcus Sida. Okay, I'll let you read it later on, maybe. He said his mic was not working, so he couldn't ask the question. And in the meantime, he left, I think. So it's about an alternative method, I think, that was proposed in the past. So there are two more questions. So let's do first Yuri, since David already asked the question. So first Yuri, and then David with the second question.
Hello, thank you for the nice talk. I have actually two quick questions. The first one is about PB plus U plus V. So if we stay on this slide, so you show that if you use PB plus U plus V, it improves with respect to PB plus U. But then if we use your idea, we use PB plus U plus V density, and then we do a non-self-consistent field calculation at the PB level. So I think you didn't discuss in the talk, but it's discussed in one of your papers. And it doesn't seem to be better than PB with the PB plus U density. Do you know why this can happen? I mean, why this happens?
Yeah. So the point is that, for example, if we take the case of low spin that we analyzed, also like the electronic distribution of the density. So we can see that the effect of U, so maybe I can, yeah, so like, maybe I can put another slide that can help. Yeah, so if you can see, for example, here, assuming that we are in the low spin state, so what we have is that like the T2G states here are all occupied while the EG star are not. So as we were saying like during the talk, the effect of U in the low spin state is that of pushing up these bonding EG states, because these EG star states are unoccupied, and so you have the effect of pushing up these EG states. And this is actually what is improving the spatial distribution of your density, as we were checking in the plot that I showed before. So when you apply V, this repulsion that is felt by the EG orbitals is somehow counterbalanced. So the EG states are no longer pushed, I mean, are less pushed up in the energy, the Constant state, EG. And so at the end, yes, the V term actually is somehow like reducing the effect of U, but still is like, let's say, not enough, like at least like we saw that in that plot that we could add or increase a little bit more U to exactly have the same density distribution found with CASP-2.
Okay, thank you. And just a follow-up question, what if we use PB plus U plus J, so Hund's J? Do you think this can be interesting to investigate, since we're talking about spin polarized cases?
Yeah, like the effect of J, in fact, like could has to be tested. Actually, in the formulation that we are using, we have this effective U term that actually is the difference between U and J. So it would be interesting to test the effect of J, and has been shown that actually the DFT plus U plus J functional, in fact, if it improves for example, the deviation from linearity, at the same time, if we compute, for example, the static error, so if we like compare if we calculate the effect and the static correlation error in this system, then U would worsen the result while J would recover the correct description. So of course there is there could be an effect of J in these systems, and it's something that has to be explored. Yeah.
Thank you.
Okay, so let's finish with the question of David, I propose.
Oh, just not even a question, but just to flag a PRL link that I left in the chat. It's a paper by Gould and Pitalis, and about Matteo's question of how do you even decide what is density-driven error and what's correlation due to the state more than the density. So the guys in Australia are thinking a lot about that, and actually how you quantify that and define it, in case it's of any interest.
Okay, thank you. Yeah.
Can I just say something very briefly
Sure.
to comment on, to complement, let's say, the answer to Mathieu, because it kind of gives the impression that we don't diffusion Monte Carlo. I think in fact, we saw a lot of deviation among diffusion Monte Carlo calculations. So as Lorenzo said, Droghetti shows very nicely. And what we saw is that, in fact, when you go to CASP-2 calculations, there is the CASP-2 calculations very stable among the different studies, okay, assuming the same active space 1210 that we are using. And that, when we use the CASPT2 corrected cable cluster calculations, our results are very, very nicely in comparison with the cable cluster perturbative triple, so which are expected to work well for weak ligand fields with the almost no multi-reference character. So that's why we kind of justify our choice. That's it.
And the Monte Carlo people claim they have all these fancy techniques for backflow and so on to correct the nodal surfaces. So I always imagine that they're using the very best technology, but maybe this is already too big for that kind of thing.
I don't know.
No, neither do I. We need to get another talk on the topic.
Andrea was here a second ago, but I don't see him in the attendance now. Actually, Drogetti, I mean.
Oh yeah.
Yeah, people maybe have other meetings. I don't know. I think it's a good point maybe to stop. It's almost 3 o'clock. So thanks a lot, Lorenzo, for the nice talk. It drew a lot of interest.